Look, in the last 3 videos, we've learned how to use the chain rule, how to calculate the derivative of the inverse function, and how to find a derivative of y equals natural logarithm of x. And look, the knowledge of these 3 rules can actually allow us to find derivatives of all exponential and logarithmic functions. Okay, so let me demonstrate to you this, but let's first start with the simplest case, and of course we will be making them more and more complex as we go. Okay, so we're going to start with the function, with exponential function, natural exponential function. So now what we are deriving is exponential function rule. So we've got a function y equals f of x equals e to the power of x. But look, what do we know about this function? This function has an inverse function. An inverse function for this one is x equals to natural logarithm of y. Okay, and look, this knowledge is enough for us to actually find derivative of function y equals e to the power of x. So, we get that if I differentiate, I'm looking for dy dx, right? Where, of course, our y is equal to e to the power of x. Okay, and look, we know that dy over dx by inverse function rule is the same as 1 over dx dy. Why do we need this rule? Because look, here we've got the inverse function and we know what is the value of the derivative of this function, right? So, because here I have x equals to ln y, I know that the derivative dx dy must be equal to 1 over y. Okay, but this is not enough. Look, we also know that y is equal to e to the power of x. So we've got 1 over 1 divided by e to the power of x, which of course is equal to e to the power of x. And look, this is how we find the first exponential function rule. And this rule simply says that dx e to the power of x is ex. And look, this is a very specific case that happens only once. I'm sorry. We have a function, and if e to the power of x, and if I calculate derivative of this function, it's equal to e to the power of x. Look, this shows us again how important number e is. Okay, so now we're going to start generalizing the rules we've already obtained. We've got logarithmic rule, and we've got exponential function. Right? Let's start with exponential function because it's easier. And look, now let's consider more complex case. Look, now we've got that y is equal to e to the power f of x. Look, so here is a case where e is taken to some complex power. For example, we might have a case with that e is taken to the power 3x squared minus 2x plus 1. Look, in such case, we can no longer use this rule, right? But as it turns out, it is quite easy to obtain the rule that is very useful over here. This time, we're going to use for that the chain rule. And look, what am I going to do here? Look, I'm going to define that u is equal to f of x. So now let's go through what we've got over here. We are looking for derivative, of course, dy dx. It is equal to dx times e to the power f of x. But now look, I'm replacing f of x with u. And look, I can always, of course, multiply it by 1 because du over du is 1 and change the order of multiplication here, right? But this is exactly what is told to us that we can do through the chain rule. So look, I can rewrite this as du e to the power of u times du dx. Look, again, you see that those two cancel each other out, and if those two cancel each other out, we are getting exactly the same expression as here. And look, now, how much is that? Derivative of eu with respect to u is eu, right? Like derivative of ex with respect to x is ex. So we've got e u times du dx. And look, instead of writing du dx, what can I write? Look, this is derivative of f of x with respect to x. I can write it as f prime of x. And I multiply it now by e to the power f of x. And this is how we get another exponential rule. If we differentiate e to some power f of x, we simply take the function that we've got over here, we calculate its derivative, put it up front, and we multiply it again by exactly the same expression. Okay, so now that we've got this, let's go to logarithms. And look, in case of logarithms, inside of the logarithm, we can also have a more complex function. So, in this case, we can also use the chain rule to find the derivative. Okay, look, now we've got y equals to natural logarithm out of f of x. So, if we would have, for example, natural logarithm of 3x squared plus 2, right? Again, we cannot use the rule that we had before. We need to try something different. And look, we actually gonna use exactly the same strategy we've used over here. I'm gonna substitute fx with u and use it. And thanks to that, I will be able to simplify this and use the chain rule. So again, we've got the dy dx, derivative we are looking for, is equal to, look now, it's d dx ln u. But now, by the chain rule, we know that this is the same as d du ln u times du dx. Okay, and now look, derivative of ln u with respect to u is 1 over u. Du dx, du dx, so we've got, let's keep it, du dx. Now, instead of u, I can write f of x. Instead of du dx, I can write f prime of x. So, what we get as a result is expression f prime of x over f of x. And look, this expression actually represents a growth rate of a function that we are going to discuss in the future, but not in this class, in dynamic economic analysis. Okay. So, we get out of this the derivative of ln f of x is equal to f prime of x over f of x. Okay, and look, thus far, the only type of logarithm and exponential functions we were dealing with were natural logarithm, so logarithm with base e, and of course, a natural exponential function. So the base also was equal to e. Now we need to go beyond that. What does it mean? Look, we're going to start with the function y equals f of x, which is logarithm with base b out of x. So we're going to generalize what we've learned to the case where b is any acceptable number. Of course, b must be between 0 and 1, not including them, or it can be higher than 1. Okay, and actually, in order to deal with this specific case, I need to introduce to you one logarithmic rule that we actually haven't covered before. And look, that rule states that if I have logarithm with base a out of b, it's the same as logarithm with base c out of b divided by logarithm with base a out of b. Okay, and look, now knowing that we can perform this transformation, let's resort to the type of logarithm we know how to deal with. Because now I can transform this into ln x over ln b. Right? Here we've got the same logarithm. Oh my god. Ln c, I'm sorry, here, out of a. Oh, I'm sorry, it's really late. So, remember, those two bases, of course, must be the same. And here we have the argument inside the logarithm, and at the bottom, we've got the base of the logarithm. Okay, so now, knowing this, of course, we've obtained that. And look, here we've got natural logarithm. So logarithm with base e, because of course, if I change the c to e, it still works. And now argument x is on the top, base b is on the bottom. Okay, and now let's go back to our more traditional approach to calculating derivatives, which is through their definition. So, I've got here, I want to calculate derivative of f prime at n, which is equal to limit with x approaching n out of f of x minus f of n divided by x minus n. Now look, this, of course, if we utilize this information, is the same as limit with x approaching n out of a logarithm with base b out of x minus logarithm with base b out of n divided by x minus n. Look, but now we also said that these two expressions are the same. So I can rewrite it as a limit with x approaching n out of ln x over ln b minus ln n over ln b divided by x minus n. Okay, and look, ln b is a constant. B is a given number. So if I take a natural logarithm out of some number, I'm also going to get a constant number. So what I'm going to do right now is I'm going to take it out of this out of this fraction. So look, I'm getting that this is a limit with x approaching n out of 1 over ln b times ln x minus ln n over x minus n. Okay, now we remember that limit of a product is product of two limits, so we get that this is limit with x approaching n out of 1 over ln b times limit with x approaching n times ln x minus ln n over x minus n. So, what do we have over here right now? Look, limit of a constant is the same constant, right? So this is 1 over ln b. But more interesting thing is what do we have over here? Look, this expression is simply the definition of a limit of the natural logarithm of x with x approaching n. So we know already, because we've calculated it in the previous video, it's equal to 1 over n. So what we get as the result is that this limit is equal to 1 over ln b times n. And through that, we obtain another logarithmic rule. We get that derivative of logarithm with base b out of with base bx is equal to 1 over ln b times x, right? Because now n can be any number, we can replace it with x. Of course, any number in that domain. Okay, and look, now that we've established that derivative of a logarithmic function with base b, we can do the same for exponential function with base b. Why? Look, because if y equals to b to the power of x, where of course b can be any number, acceptable number, so it's either between 0 and 1 or between 1 and infinity, then what is the inverse function for this function? Of course, inverse function in this case is x equals logarithm with base b out of y. Okay, so what should we do here? Look, I want to find the derivative dy dx. I know that this is equal, through inverse function rule, to 1 over d x over dy. But dx over dy is actually derivative of this function that we've just found right now. But remember, I just switched y and x because we are interested in this function. So how much is it going to be? No, it's going to be 1 over ln b times x. Times y, of course. Oh, sorry. Times y. So how much is that? Well, if I divide 1 by 1 over some number, I'm getting that this is ln b times y. How much is y? Y is bx. And this is how we obtain yet another rule. We know now that derivative of b to the power of x is equal to ln b times b to the power of x. Okay, and look, both of these functions both of these derivatives that we've seen over here and over there can be generalized using the chain rule, right? The way we did this a couple minutes ago. So now we've got that y is equal to logarithm with base b out of f of x. So now inside the logarithm, again, we've got some function. So what do? Well, what we're supposed to do, right, is to replace f of x with u. Because now we can easily use the chain rule. Okay, give me just a minute to erase the blackboard. Okay, so we want to find dy dx. Our dy dx is dx, because our y is this, is logarithm with base b out of u. And now, again, using the chain rule, this is the same as du, logarithm with base b u times du dx. So, how much is that? Well, we've just calculated this, right? We know that this is equal to ln b times u. 1 over ln b times u. Now, and we have du dx over here. And now look, we know that u is equal to f of x. And we know that du dx is derivative of f of x with respect to x. So this is f prime of x. So we get yet another rule in which we get that this is f prime of x over f of x. Maybe let's write it in proper order, times ln divided by ln b times f of x. Okay, so what we get over here, maybe I'm gonna write it here. Oh. Yeah, the dx out of logarithm with base b out of f of x is equal to f prime of x divided by ln b times f of x. Okay, and there is only, of course, one more generalization to go. We need to find derivative of y equals b to the power f of x. And again, we are using the same trick. U is equal f of x. Now, what we are getting out of this is that dy dx is equal to dx b to the power of u, which by the chain rule we know is the same as du bu times du dx. Okay, and look, we've already know what is derivative of bu, right? Because we actually have the formula over there. This is going to be ln b times b to the power of u times du dx. Okay, so this, now the only thing is to substitute for u. So we've got that this is ln b times, and look, du dx is again f prime of x, and at the end we've just got b to the power f of x. And this is giving us the final rule that dx b of b to the power f of x is equal to ln b times f prime of x times b to the power f of x. Okay, so now let's summarize all the logarithmic and exponential rules that we have covered thus far. So, first we've established that derivative of ln x is equal to 1 over x. We've also established the derivative of e to the power of x is equal to e to the power of x. Then we found that derivative of ln f of x is equal to f prime of x divided by f of x. Now, then we've got here that derivative of e to the power f of x is equal to f prime of x times e to the power f of x. Okay, then we had two more rules. We found that derivative of logarithm with base b out of x is equal to 1 over ln b times x. And over here we found that this is d, that d dx logarithm with base, b to the power of x is equal to ln b times b to the power of x. And finally, the last two rules is logarithm with base b out of f of x is equal to f prime of x over ln b times f of x. Then derivative of b to the power f of x is equal to ln b times f prime of x times b to the power f of x. Okay, let me put this upstairs. And look, I do not expect from you to be able to do every derivation. But what I definitely expect from you is to know how to calculate each of these derivatives and each of the formulas we derived previously, final formulas by heart. But look, when you're gonna be learning them, look at the similarities between these formulas. Look, if I'm gonna take formula number 2 over here, logarithmic formula number 2, and I'm gonna combine it with formula number 3, I'm right away getting formula number 4. And look, the same is true for formula number 2 and formula number 3 for exponential functions. If I combine those two, I'm getting formula number 4. So look, there are some similarities that we can notice in easier to remember them more easily. For example, look, here we are dividing by ln b. And look, over here we've got inverse function, so there is not a surprise that here we are multiplying by ln b. Okay, so knowing all this, the only thing left is to go through different examples. Okay, so let me now demonstrate how to use these rules, which actually makes the job of finding derivatives extremely easy. Okay, so let's just say that y is equal to natural logarithm out of 4x to the power of 3 minus 2x to the power negative 1 plus 3. Okay, so this time I need to use logarithmic rule number 2. So look, I'm starting by drawing a fraction bar, and what do I do? First, I see that the same function that is inside the logarithm, I need to rewrite into the denominator. So I've got that this is 4 x to the power of 3 minus 2x to the power negative 1 plus 3. Now, what should I have in the numerator? Derivative of this function. So this is 12x squared plus 2x to the power negative 2. And we're done. This is it. This is how we use this rule. Okay, so what if we've got now y that is equal to e to the power 7x squared plus 14x. Look, again, we just look at the rule, and what do we see? dy dx, so derivative of this function, is given by, first, I'm calculating the derivative of the function that I've got in the exponent. Of course, remember about using parentheses. How much is it? 14x plus 14. What do I need to do next? Rewrite exactly the same function. And this is it. We've solved this problem. Okay, now, what if I have a function y equals logarithm with base 5 out of x? Well, then, of course, I'm using this rule. We get that the dy dx in this circumstance is equal to 1 over ln b, which is 5 times x. Again, very easy to use. Okay, now, what if I've got y equals 1 over 3 to the power of x? Now we're using the third rule for exponential functions. So we've got the dy dx is equal to ln b, so ln 1 over 3 times 1 over 3 to the power of x. Again, as you see, application of this rule is extremely easy and straightforward. Okay, now we need to use the last two rules. So let's just say that now we've got y equals logarithm with base 7 out of 4x to the power of 3 minus 2x plus 1. Okay, so of course now we are applying rule number 4. And what do we get over here? The derivative dy dx is equal to, we start by fractional bar, and what we'll definitely have in the bottom? ln 7. Right? Now, I multiply it by by the same function for x to the power of 3 minus 2x plus 1. And in the numerator, over here, I need to put derivative of this function, which is 12x squared minus 2. Again, very easy. Okay, so the application of the final rule. What if we've got y equals, I don't know, 2 over 3 to the power 7x to the power of 6 minus 4x to the power of 2 plus 3. This is all in the power. Okay, look. Now, of course, we are applying this rule. So we've got the dy dx is equal to, first, natural logarithm of b, then times derivative of this function, which is 42 x to the power of 5 minus 8x, and now we multiply it by exactly the same expression. So 2 over 3 to the power 7x to the power of 6 minus 4x squared plus 3. Okay, so now of course you need to practice it a lot, because like everything in mathematics, our knowledge comes from practice. We need to not only understand how we get things, but we also need to practice a lot. And look, if you calculate for all the derivatives 100, 200, oh, definitely 200 different examples, you will know how to do it for the rest of your life. Okay, so this is it about rules of differentiation. Now, in the next video, we're going to move to higher order derivatives. So what happens if I differentiate the same function more than once? Okay, take care.